And so the sustainability lecture should really touch upon almost all, actually, if not all, of the material systems that you're all proposing, more or less, not specifically each, material system and composition, but the umbrella will cover the end applications like lithium ion batteries, sodium ion batteries, conversion type materials in the discussion. Okay, so it's the minimum guidelines are really my attempt at trying to bring everybody onto the same page so that as you're comparing the different technologies, there's a baseline to do so. So that's the sustainability assignment that's coming up in the peer review. And then of course, once we hit the work plan assignment, that's when the due dates will actually switch over to Monday. To accommodate the major assignments that are due around this time on Friday. So I didn't want to basically, put undue pressure on these due dates, unnecessary pressure. The other thing I wanted to mention as a broad strokes comment regarding the assignment, the literature reviews that were turned in, and I will more specifically write up my comments and email that out for those that turned in the assignment. You obviously all got my specific feedback for each of your reviews, but the broad general stroke that I'll say in front of everybody, because it applies to everyone, for those that turned in an assignment and for those that have not turned in an assignment, is the selection of the literature. One of the reasons why I asked everybody to justify their reasoning, their selection, is so that you go through the practice of really selecting the journal article or the source that is most applicable, because there's so much literature on almost any material system you can think of. So how do you select the one that is most applicable to you and that is most apples to apples comparison, right? And so that's one of the reasons why I only started off with 10 sources as a minimum, but as you develop your sustainability argument and also your work plan, I anticipate that the number of journal articles and review papers and sources that you're going to use will more than triple. Okay. The other thing I wanted to mention is be very wary of journal selection itself. One of the things that I wrote in the guideline for the lit review is beware of journals that have made it onto the list of how should I say this delicately? Predatory publishing practices. Okay, so this is a loaded term, and there's a lot of room for debate regarding what signifies and qualifies a journal as a predatory, journal, or a publisher is predatory. Often it is a journal that is, part of a publisher that is for profit. Nature is also for profit, by the way. So there's a lot of nuances. Nature does not practice predatory review procedures, but I have linked to 2 lists and 2 resources that you can look up and really educate yourself on predatory style publishing. Okay. I don't want to call them outright because these journals outright, because these lists are also evolving. And that's not to say that all authors who publish in journals that have predatory practices, I'm not saying that their data is in any way less reliable or questionable in any way. But what I am saying is be very careful what you read, because the peer review process is a delicate one. And the integrity that we all have as scientists and engineers in our community is to uphold that level of collegial critique, collegial critical thought, and really give good feedback. And when we can't uphold that level of integrity, it really undermines the entire publisher, the entire journal. So that's my very broad stroke statement to follow up on, these lists. And if the journal, the article that you pick is within a journal that shows up on this list, that should signal to you that you should be extremely cautious and wary of of what you're reading, and that's also to say, just because you see a big name, a name that's recognizable in the field, and you should think surely, this person is vetted, it's very nuanced, okay? And you shouldn't let someone's reputation dictate how you think of the science, okay? You yourself as a scientist and engineer should really make that informed decision based on your foundational knowledge that you have, okay? So that's my very diplomatic way of saying, please be very selective and be very critical of what you pick, and really dissect what's out there. Yes. Ooh, I think you'd have to ask me for that. I mean, it's really up to the publisher, right? I mean, the arguments cut both ways, it's not like Nature only publishes clickbait, right? Or flashy things that will get readers to subscribe. I mean, that's obviously not the track record, right? So that's not the case, but it's really it's a business model, right? Profit and for-profit is really a business term. At the end of the day, you need somebody to process submission. You need somebody to do the administrative work, right? And that somebody needs to be paid. And whether or not a publisher chooses to maximize the profit margin or not, that's a whole nother business entity, area that I'm not an expert in. I don't run a publishing company, but what I do know, and in terms of interactions with publishing, is that as an author, at the end of the day, you have to make a decision as to how to disseminate your information, right? All for-profit and nonprofit publishers run by societies, or not-for-profit run by society, like society journals, or like the AAAS, they have that sort of organization. You still have to make a decision as to how to disseminate your information, regardless of profit or for-profit, because eventually, at the end of the day, these journals, most of them are still behind paywalls, right? I mean, the Ohio State University has to pay a license fee to access journals, and that's one of the reasons why you have to go through a proxy if you're not on the internet on campus, right? And so then you have to wonder, what is your role as an author? You, the general you, everyone in this room, what is your role as an author if your work is federally funded by taxpayer dollars, right, through a government agency, to then disseminate that to the public if it's behind a paywall, right? So then do you publish in a open source, open access type journal, but then somebody has to absorb that publishing costs? And the costs can range from the low 1,000 to the high $3,000-4,000, depending on color, ink, and whatever other details that that's specific to each journal. So at the end of the day, it's a business. And so It's one of those things where there's a historical model and then there's personal decision as to what to do with that. And if you don't have the funding to publish and pay $4,000 or however many $1,000 per article because you need to buy chemicals with that, that is just, you know, that's a decision that may have already been made for you. But then that goes back to something that's well beyond just personal decision. It's infrastructure, you know, and this goes beyond, you know, these types of costs go beyond just scientific discussions, like servers for hosting data afterwards. If you want data to be publicly available, who's going to pay for the servers to host this data? Should it be the author? Should it be the organization? Should it be the funding organization? I mean, these are very high level discussions that need like very large, wide, impactful policies that affect everyone. You know, so that's all to say, it's not an easy answer. But yeah, so anyway, that was my very broad strokes comments. I'll follow up with more detailed but still general comments because you've all received my specific comments. Correct. Okay, so with that, I'm going to proceed with the sustainability discussion unless there's any other questions following up from last time. Okay, so I'll continue with the discussion of life cycle assessment, specifically answering the questions of, you know, looking at raw materials and assessing, you know, if they're critical materials or not, and also evaluating the energy impact of the extraction, refinement, waste processing of the raw materials. And then once you have your raw materials, you know, one has to consider the bottlenecks in terms of materials production and then also, you know, fabrication for the eventual end use. So that's what we're going to talk about. Now, before I also corrected myself, or at least I specified when I say, you know, critical elements, I just meant, you know, important elements. But there is an actual technical definition to what a critical element is. And so this was taken from a rather old report now from the Materials Research Society. But it does define very well what an energy critical element is. So this report was put together by a number of Materials Research Society members that have been doing the, you know, doing research in the energy field for a long time. And they've identified these critical elements as a whole class of materials that are critical. Okay, but what does that really mean? Why are they critical? Well, they satisfy a number of criteria, such as they're just rare. It's, you know, there's just so low concentration of them in the Earth's crust for us to even mine, much less mine successfully. You know, there are regions that we have difficulty getting to, but beyond that, you know, even if we could get beyond the geopolitics, you know, is there enough of this raw material to even dig out of the ground? So the rarity of the element in the Earth's crust makes them a critical materials. Low concentration for economic extraction. So they're just too low and really energetically and costly to even extract. So no one has proposed the use of tellurium and rhodium, but you know, these elements are, particularly rhodium and the platinum group, are heavily used in the fuel cell industry, which, you know, when you think about energy storage, fuel cell technology goes hand in hand with battery type vehicles and battery type energy storage. But that's not the point of this class, but I just thought I mentioned it because fuel cells come up a lot in discussion when compared to battery technology. Cobalt, we've been talking a lot about because you probably have also seen it in, you know, news articles and the media, that cobalt is a critical material because there are some geopolitical issues. And what do I mean by that? I mean, Cobalt is mined typically in a region that, in a country where a lot of the mines are not owned by citizens of that country. So there's an added layer of the ownership of the mine are actually located in other countries. And so then you have, government policies to deal with. You have two government policies to deal with, and it's a lot to take on. And then environmental damage. So, if you have to, I don't know, really disrupt the environment to extract that, let's say you want sodium chloride or lithium chloride out of the ocean. Okay, that's obviously going to affect the pH. If you start extracting those salts at a scale that is necessary to actually put lithium into, the 60 million cars that are projected to be electric in 20 years, then, that has environmental impact, like direct environmental impact of, marine life. So the elements that are highlighted here, right? So the cobalt, the platinum group, which is really more so for electrocatalysis and like fuel cell technologies, those you come across a lot because platinum is such a good hydrogen evolution reaction catalyst, as well as an oxygen reduction catalyst. Now, some of these elements you've seen probably more in the discussion of photovoltaic compounds. So gallium arsenide doped with selenium and tellurium. So these are elements that are critical. And so we have to think about, okay, well, if we know it's critical, do we just accept it and just try to develop technologies that minimize those because there's no other material that can meet the performance metrics? In thermal electrics, sometimes that is the case. If you want high figure of merit, it's difficult to find another element that would replace the composition that you've already developed. Okay, so that is, in terms of space, that's like aeronautics. That sometimes is the case, and so you have to think about, well, if it's not possible to replace with a base metal or something that's more earth abundant and less critical, then how do we make the device more efficient? So sometimes, you have to think about that, or you just try to abandon ship altogether and just say, well, this is just never economically going to be viable, and I just have to develop something else and, jump ship. It's just too cost prohibitive, unless there's like one buyer like NASA, so that's the discussion that's going on. In terms of, elements that are pertinent to energy storage, specifically lithium ion batteries conversion, lithium, like lithium sulfur conversion type technologies, germanium, selenium, we've seen these elements pop up a lot. Germanium's been proposed as a anode conversion type material for the anode for lithium batteries, but of course, it's not as earth abundant. So if you look at this plot, you see abundance in terms of the atoms of elements per 1 million atoms of silicon, and it's normalized to silicon because sand is everywhere. So clearly here, these are the elements that are attractive because they're high in abundance. The rare earth elements are, down here. Obviously, osmium, iridium, we've seen iridium come up quite a bit as model systems for anionic redox. And while they're great compounds for anionic redox, clearly it's not economically or advantageous in terms of earth abundance to really pursue commercialization of these types of materials, right? Iridium containing compounds. So, you look at these and you think, okay, well, it makes sense why someone would pick silicon to explore as anode, to develop as an anode for lithium ion battery technologies. So then you also think, well, it also makes sense why someone would pick sodium relative to lithium. It would also make sense why someone would pick magnesium and aluminum. And so you see all of these now chemistries being heavily explored as not only as increasing energy density, right? Transporting a +2 charge versus, just +1 for lithium is attractive for doubling the capacity, but of course there are additional challenges of developing suitable, stable electrolytes that come along with developing a new energy storage technology. So in terms of life cycle assessment, we also think about where the raw materials come from. And typically, we dig something out from the ground. You're going to have to purify that raw material. And the purification process requires a lot of high pressure and a lot of just energy put in to purify to the metallic form even. So you could also collect the salts from brines, and that's more typical for lithium. So if we look here of the relationships of where these metals come from, I've highlighted a few elements that are germane to our discussions today. So in terms of lithium, you see here, typically the source is, lithium carbonate, and you obtain that from lithium brine, and then you purify that to get rid of all the other salts in the lithium brine, and you get lithium carbonate out. And then from there, you can causticize to lithium hydroxide and then start reacting lithium hydroxide to make, lithium cobalt oxide, say, or what have you. The other, considerations is if you have to, how much purification do you need? So from lithium brines, it's, pretty single source, your lithium comes out of that. But typically for, nickel, manganese, and other metals, you have to really go find them, and they typically exist in ores with other metals. And so the purification, to get nickel away from iron, that kind of thing, is energy intensive. And so, so that takes quite a bit of effort to go from cradle to gate there. So it's not always so obvious that, if you want to nickel, that you just go to a nickel mine, right, in Sudbury, Ontario, Canada, right? Although if you went to the nickel mine, you'd also be visiting a neutrino research facility, because they have to go so deep into the ground to find these neutrinos that actually you go down the same chute as the nickel miners, which is pretty interesting. But anyway, I digress. In considering how sustainable a process is for extracting raw materials to, the starting precursor that you need to make your cathode and your anode and what have you, is we also need to think about the energy and materials changes, and also the pollutants that are byproducts of the purification process, the extraction and purification process. So in terms of discussing normalized terms so that we can compare apples to apples, one of the points of consideration for comparing, how energy insensitive and how polluting the extraction of a certain metal is, one compares the global warming potential, and that's in units of the number of kilograms of CO2 equivalent per kilogram of material that is produced. So here you see in this table that rhodium the extraction of rhodium produces the highest amount of CO2 equivalent. Now it's CO2 equivalent because there are other greenhouse gases that are also produced, and they have different equivalents to CO2. So in terms of global warming, CO2 is normalized to 1. But if you produce methane as well, its impact is about 26 to 28 times that of CO2 in terms of global warming, in terms of the IR, absorption. Okay, and then if you have N2O on NO, then that's about 200 times more. So you can produce 1/200th of of N2O relative to CO2, but they have the same amount of impact. Okay, so it's normalized to CO2 equivalent when you're talking about global warming potential. And then there's also CFCs and HFCs and other gases that come along, and they are also of concern because if you look at the CO2 equivalent, that's about 1,000 to 10,000 times as impactful in terms of global warming for CO2 equivalent. Okay, but none of you have proposed rhodium. We're more interested in, let's say, the NMC, the 3D transition metals, and you can see here that the lower content is, it's relatively, I wouldn't say benign, but it produces less CO2 equivalent per kilogram of metal that is produced, right? For the cumulative energy demand. So this is the direct and indirect energy used throughout the life cycle, right? And so this is the energy content that is consumed during the extraction, during the manufacturing, the disposal of raw and any other, auxiliary metals, materials that come along with extracting a certain type of metal. Here you see, once again, rhodium is, produces, requires a lot of energy in terms of megajoules equivalent per kilogram. And so how do you then, input all these thermodynamic parameters? Well, if you look at an example of, let's say, just produce like a fuel cell, a reaction where you're just putting in, hydrogen, oxygen, you often see these terms like the higher heating value or the lower heating value. And these are terminologies that you come across quite often when you read about energy estimates, of like how much is it heat to how much is it going to cost you to, heat a building, that kind of thing. You look at the upper and lower values. So for this reaction, if you were to produce H2O under conditions where you can produce H2O liquid or H2O gas, you can look up the thermodynamic parameters in just like a table that's been tabulated. And basically you're looking at the difference in enthalpy where it's just products minus reactants. Okay, and so you can get the lower and upper values this way. Okay. So then there are other considerations like acidification, right? So this is particular when there is SOx and NOx involved. So for producing these elements, if there is an increase or decrease in the pH due to the generation of SO2, NO, N2O, and NH3, NH2, then that's all quantified in kilograms of SO2 equivalent, because as we know, sulfuric rain is quite acidic, and that impacts the environment in a negative way. So we also think about the acidification potential. So here we see nickel is a little bit more than that of cobalt, interestingly enough, the way that these elements are mined. Whereas iron, manganese, and chromium are less than that. Vanadium is more than the middle 3D transition metals, but still less than, say, scandium or nickel and copper. And that's just because of which type of ores they're in and how much it takes to extract these elements and the gases that are evolved. Now, eutrophication. So this is standardized by the amount of phosphorus that's in the system. So too much phosphorus will induce excess algae growth. And we've all seen the latest news of lakes in the region, in Ohio, that have been affected by really large algae blooms that suffocate the fish and really hurt marine life that's there. And that's because of fertilizers and increased phosphorus content. So when we extract these materials from, from the ores and go through purification, a lot of times, phosphorus will be produced. And of course, that will then basically suffocate the fish due to eutrophication. Okay. And then there's also human toxicity impacts. In terms of normalization, it's the morbidity count. So that's, how many people that suffer from diseases in the total human population. And so there are numbers associated with this. And so what you see here is that copper and zinc are actually higher than that, have higher human toxicity impacts than that of nickel, which is higher than that of manganese, iron, cobalt. Right? So even though we've been talking about cobalt in terms of mining and geopolitical issues, these are some of the other terms that these other quantities that we can still compare to sort of standardize sustainability. Okay. Now, going back to the cobalt pipeline, we talked about, right, the geopolitical issues, as in cobalt mines are heavily concentrated in one region. And thus, if that's the case, then you're reliant on the stability of the local government. You're dependent on policies that are friendly to, international trade. And so diversity and diversification would be attractive, and so it would also lessen the swing of cost. It's really the swing in the cost that makes the economy unstable, right? You can't predict if the cost of lithium tomorrow or next year is going to increase linearly or decrease linearly. If it's just going to be a massive swing, that really affects manufacturing, that affects everybody down to the consumer, at the end of the day, right? And so diversification and reducing cobalt concentration in cathode materials, these are some of the driving forces for that. And you really see the dependence on the Democratic Republic of Congo in this chart here. You could see that, from these few mines in the DRC, that they are responsible for the majority of the cobalt that ends up in electric vehicles. Okay. So we're heavily reliant on one region. And I should also say the companies that run the mines in the DRC are not owned by those who live in the DRC, the citizens of the DRC, mostly owned by China. So there's a layer of complexity dealing with multiple, international relations there. And you could see that in this chart here. Okay. In terms of nickel mining, since we've been heavily talking about, nickel-rich compounds, increasing the nickel content, we take a look at, okay, well, we switch to that. Which other countries are we going to have to engage coming from the US? Well, here you see the production, mostly Indonesia and Australia. I know we're already dealing with Australia for lithium. So there's that added layer in Brazil, Russia, Cuba. These are the countries with the most number of reserves. So this is where these are the countries we have to engage in if we're going to try to get enough nickel out. Of course, Canada, as I mentioned, but it's not in the top 5 as you see. The price doesn't fluctuate as much as you can see here over the last 3, 4, 5 years. So relatively stable, which is good. In terms of producing nickel, really, there's a lot of sulfur that's going to come out, sulfur oxide that's going to come out. So acidification is going to be a really key parameter for discussing the sustainability of getting nickel out of these ores. And you can see I've put here, some of the techniques for producing nickel. Just like shared Gordian refining. So basically, it's very high pressure, high temperature smelting procedures that just then requires you to clean the intermediates up with acid. And so there, acid leaching is a real containment, and leaching is really a problem, okay, to deal with. So we've talked briefly about lithium and how it's really not we're not going to run out of lithium anytime soon. And so it's really not about the reserves, because there are plenty of it. You can see the dominant player is Chile. And in fact, the dominant region is this triangular region here called the Lithium Triangle, that composes of Chile and Chile and Argentina. But Australia is also a dominant player, and so is China. And in terms of cost, it's actually gone down over the years because of the efficiency of the technology for extracting lithium from lithium salts. So that's, promising, but it still takes a lot of energy to go from, lithium that's contained in the lithium brines, these, vats and vats of just salt plains, essentially. And then to get it to the form of, either lithium carbonate and then lithium hydroxide for battery use. Now, in terms of the amount of lithium that is used for battery technology, it's about 70% last year. So the amount of lithium that's extracted from the ground that goes into battery is predominantly for battery usage. So, if we can reduce lithium in its usage in sort of way, it really does swing, it has a lot of impact when it comes to the flow of lithium. Now, when it comes to the discussion of how to extract and where to extract lithium from, Chile is obviously the dominant player, but we in the US still has a lot of regions where lithium could be extracted, and maybe at a level that's more energetically benign or not as costly, and that really has to do with the use of the surrounding conditions. So there's quite a bit of lithium salt that's in the salton sea, and there are some geothermals that are there that can be used. The heat, the high temperature, and also the pressure that's already built into the natural system can actually help with the production of lithium carbonate that is, not as energetically intensive or as long. These lithium salt plains that you see here, you really just have to wait a while for it, but basically water to evaporate, and then you purify and get your lithium cobalt out. So it could take months and years to really harvest the lithium salt to finally then, get it into production. Okay. Interestingly enough, if you have not heard of the Atacama Salt Flat, that's also the Atacama Plains are also home to the large telescopes that, of course, have revolutionized our understanding of the universe. So a lot is going on, terrestrially and I guess extraterrestrially, intergalactically. Okay. Okay, so we've heavily concentrated on lithium-ion battery technology in this first third of the lecture series so far, but there's a lot of energy storage technologies that are out there, right? And so because we have some limited time, right, I'm going to focus on sodium ion technology. I'm also going to focus on lithium sulfur, as you see here. But potassium ion, potassium conversion batteries are actively being studied. Multivalent batteries like multivalent cation batteries like magnesium, calcium, zinc, aluminum. They're all there. And of course, fluoride-ion batteries are also being investigated. Iron air is coming back. It actually has come back. But that has been looked at by NASA back in the 1960s already. So there's a lot of work that's already been done that we sort of put to the side a little temporarily as lithium-ion battery technology really took off, 91 by Sony and, well, 80s by several groups, and then commercialized in the 90s, and it's really taken off now, but there's a lot of alternative energy storage technologies beyond lithium-ion batteries that are quite exciting. Okay. And depending on what your needs are, the technologies can satisfy, either energy density or volumetric energy density, gravimetric energy densities, or in terms of temperature, all that sort of thing. So it's not, the energy landscape, it's quite open for all this. So if it's so open, how do we compare, really compare apples to apples? And so Argonne National Lab has come up with a systematic way of modeling, how to translate raw materials and cost of materials, the costs of the battery or a pack at the end of the day. And so this article is, or sorry, I should say this report is the third edition of the model. There are previous models. This is the BatPaC 3.0. And if you download their spreadsheet, you can really play around with, if I can change efficiency by 1%, let's say coulombic efficiency, or if I can change gravimetric capacity of the cathode, of the active material by X%, how much is it going to impact, the cost down the line? You could really feed all your assumptions into the spreadsheet, and it will come out and give you things like, how do you think about, materials input, direct labor per pack, capital equipment, assuming a company is going to make 100,000 packs a year. What about the building and the land? I mean, it really takes into account the entire, system, the entire from like A to Z, and not just how do I get cobalt out? And if I can decrease cobalt cost by, X%, then my active material will be a little bit less expensive or something like that. It's really a very holistic view. So there's a lot to play around in there. And so this is basically going to be the model that's going to be used going forward. So the assumptions are all built in. And so you can compare from, one system to the next. By that, I mean, like if you compare a lithium-ion battery with a graphite anode versus lithium-ion battery with a lithium anode versus, let's say, lithium sulfur. These are very different technologies, right? I mean, one is an insertion mechanism, one's a conversion with the lithium anode, and then another one is a totally different conversion cathode. So how do you compare all the metrics and say, what is eventually the cost per kilowatt hour at the end of the day? That has to be, $100 or something like that to be viable, right, commercially. So how do you translate that? That's built into this model. Okay, so this is another screenshot of just how detailed, all of these assumptions are. You could also change the C rates, things like that, and change the thicknesses of cathodes to really go into detail or that. So the next set of slides will really focus on trying to do just that, trying to compare, the current technology that we have, lithium-ion battery technology, the costs associated with that, breaking down each, in terms of, the materials breakdown costs, but also comparing that with, let's say, sodium-ion battery technology, and then also lithium sulfur, which are the top two. Okay, I was going to close the door, but now I'm just going to shut it on people. So I'm not going to do that. So we're just trying to focus. Okay. Okay. So in terms of the cell configurations, one of the reasons why we need a model is so that we can try to normalize as best as we can, because the geometries are so different, right? In going from, let's say, a liquid electrolyte system, you can see the different thicknesses of materials here, And when you go to an all solid cell, the thicknesses are, vastly different. And the composition and the composite makeup is vastly different, right? So how do you compare these two technologies when one, you have a porous separator here, and here you don't have that separator, right? So if you're doing normalization due to say specific energy, you're dividing it by the mass. That's not as difficult, but in terms of like switching conversion technologies altogether, that is a little bit difficult. Okay, so the first set will be comparing sodium-ion batteries to that of lithium-ion batteries, and we're going to try to be as standard, compare apples to apples as best as we can. So in terms of starting out, which cathode do you even start with? Okay, so in this model, let's say we start off with something like lithium manganese oxide for a cathode and graphite as the anode. So then, in terms of going over to the sodium-ion battery side and choosing a sodium manganese oxide cathode, you obviously can't translate the graphite anode into from lithium ion to sodium ion batteries, right? So here the typical carbon that's used is hard carbon or disordered carbon, right? Okay, so let's say you do that. If you look at the costs, we're gonna calculate how you get to $2,981, let's say. So if you make the assumption, how much is my battery going to cost if I have to design a battery pack that is 7 kilowatts and 11.5 kilowatt hour in capacity, in energy? Okay, well, where do these numbers come from? So this is a model that is used for trying to estimate, what is going to be the cost of your battery for, let's say, powering a house, the number of appliances that are in the house and the energy needs for a single family home, particularly in Europe. It's going to require 7 kilowatts, an 11.5 kilowatt hour battery. Now in the US, if you look at how much energy we need, you could see now it's a different ball game, right? I mean, the average US household requires 33.7 to 34 kilowatt hour battery. Europe and China consume a little bit less, just for comparison. Okay, so in terms of the cost, you can see here the swings really impact how much your cell is going to cost from year to year. If you were to make this battery in 2015, your starting material, lithium carbonate, would only have cost you $6.50 per kilogram. If you use starting material in 2016 to manufacture your battery, then it would have cost you $20 per kilogram of lithium carbonate. So you could see the swing really affect what the consumer is going to have to pay at the end of the day. And then it swung back to $13.90 in 2017. Okay. And in terms of the percentage, of lithium in the entire material system of the cell versus the complete battery, it's actually in terms of the cost, it also swings. It goes from like 4.5% to 13% to then 8%. So depending on which year it is, this could be a significant cost or it could be not a significant cost. Okay, so there you have it. So in terms of going from lithium to sodium, it's been argued, right? If you, based on what we just discussed, the availability of sodium, the earth abundance of sodium is greater than that of lithium. In terms of the costs, it is less, but even more so, by changing geometries, you're also affecting the copper and aluminum costs. Now, the current collector costs, because in going from lithium to sodium ion battery, you can now use aluminum current collector instead of copper current collector that you see here. So the cathode, this copper foil that's here is no longer needed. So you could see the cost going down from, in terms of just materials cost, going from $1,022 to that of $894 for just the materials cost itself. not the manufacturing of the entire, the total cost of the battery. So that's great. And in fact, copper prices also fluctuate more than that of aluminum. So now you're stabilizing the cost. So there are some attractive features already, even though the offset is now you're using an ion that is 3 times in weight relative to that of lithium. Okay, so you're offsetting some costs there of your overall cell. So that's, exciting. In terms of chemical stability, aluminum is also more resistant to oxidation, over discharging versus copper. So another added advantage, and this could help with obviously cycling life of your cell. Okay, so some attractive features at the materials level. Let's then compare different chemistries. So if you look at this very beautifully colored bar plot, what you see is a number of modeling scenarios. Okay, so what we just talked about was lithium manganese oxide with synthetic graphite versus sodium manganese oxide with synthetic hard carbon. So the costs come down to, lithium ion batteries, $2,981, but sodium ion batteries, interestingly enough, comes out to higher than that once you actually end up making the entire battery. The other 2 examples I included in here, but they're actually quite fictitious, right? So the example that's used for, let's say, going from lithium manganese oxide, let's say you switch up the lithium ion battery cathode to that of NMC 622. This, then you have to compare, okay, how do I compare NMC 622 to, and using a natural graphite, how do I compare that to, let's say, equivalent sodium ion battery technology? So this particular study sort of said, okay, let's invent some advanced sodium ion cathode. That's really what ASC stands for. Let's think of some futuristic compound, and let's think about some futuristic anode as well, like phosphorus containing hard carbon. Okay. Based on some studies that have been done recently showing that could be a promising anode. What you see is once you start crunching the numbers for the cost of phosphorus, the cost of making the hard carbon, all that, you see the breakdown it's getting closer. So your price for lithium ion batteries is coming down because NMC 622, it's higher capacity. Okay, so that's pretty exciting. So the price comes down to $2,700, and the price of sodium ion batteries also come down to $2,900. So it's about almost parity. The price differential is not as great, assuming that all these batteries perform at the level which is predicted. And then there's also going even to for more futuristic compounds that have been modeled. You see the price once again comes down a little bit more, but it's really a fictitious compound, so I don't even know. But anyway, that's all to say, just because an element is more earth abundant does not mean that the final cost will actually be less. You can close the price gap and the price difference, but it's not always so obvious, right? Just so the argument that sodium is more abundant, it's cheaper, is going to result in a cheaper battery is not true.
Yeah, that also argues like solid state batteries, just because it's solid state, that doesn't necessarily mean that it's safer than liquid electrolyte batteries. And that also be like the case, like not sort of topic. That's just something else.
Oh, so when you say safer, do you mean flammability wise or?
Right. So
Okay.
Because it's a solid state battery, that doesn't necessarily mean that it's not flammable.
Well, yes. Do you have a specific case in mind?
Not quite, but I mean, like that's just like a claim that people would generally say when it comes to like solid state batteries, just because it's solid state, it automatically safer. That makes it actually.
Well,
It's like generalization. So like, I wasn't part of like so I was just talking about generalizations that people make in the battery.
yeah, well, I would say the context of people, right? Generalized people that I've talked with, unidentified individuals that you don't know, nor have I named them, but also general strokes. I mean, my understanding and interpretation of, the discussions that have been had is that it really pertains to, the topic of flammability. Now, other safety considerations, if you're thinking about, I don't know. I can't even pull one out of my, out of thin air right now. But I think the argument for flammability, basically the liquid electrolyte causing a thermal runaway reaction is a valid one. Now, if there are other considerations beyond that particular safety issue, at least in the conversations I've had, which is a small sample size of the world, right, has not gone outside of that context. So I am interested to hear what other contexts of safety people are considering when they make statements like that. Okay, we are 3 minutes over time, so I will pick up here next time. Well, these are the details, the very fine details of how you come to the prices that are here. So maybe I won't belabor the point, but then maybe pick up on lithium sulfur next time. Because we really only have one more slide to talk about when it comes to the comparison of sodium to lithium ion batteries. So I'll pick up here just to cap the discussion and then move on to lithium sulfur regarding sustainability, not regarding the chemical reactions, although that will be coming. Alrighty, thanks everyone.